course, it's always lovely to hang out with the mathematical family. You're a big part of what makes math fun, I'd say. So I apologize if the talk title scared anyone. No random currents will be harmed during this presentation. But I was raised on the idea that any good talk on math should include at least one proof and at least one joke. And the two should not be the same. So here the theorem is a joke. So I assume that this keeps up with the rule. So what are we talking about here? We are talking about the Ising model. It has been defined a multitude of times, but just to make sure we cover all our bases. So right, we look at our classical Ising model with its two-point interaction. I am gonna, for the sake of notational ease, I'm only ever gonna write the nearest neighbor model, but everything today is also about long-range Ising. Those that know, and those that don't know would probably just get confused with needless notational flood. So this is, of course, the most studied model in statistical mechanics, roughly, and the sigmas, of course. It has been defined a number of times, so I assume that everybody's on track at this point. And of course, today I am going to talk about the random current, so I had better introduce it, even though this too has been introduced. So what's my configuration space here? Now every edge is assigned a value, which could potentially be 0. And I'm raised in a German tradition, so for me, 0 is not a natural number. So what's the probability of drawing a given current configuration, which, I mean, I will think of as a multigraph with the number indicating the number of parallel edges. This is going to be this Poissonian weight. Except you have this indicator that constrains how the multigraph may look. Namely, I want my sources to be exactly the set A, where the sources of A and are exactly the vertices for which, as Franco told us, it's the set of vertices where viewed as a multigraph, the degree of n of these vertices is odd. And as has also been discussed, the current has this property. Maybe here I should really take care. There is some normalizing constant set A, and that normalizing constant plays a role. Because the Ising correlations, again, as Franco informed us, sigma A is just by definition the product over vertices in A, sigma V. And the expectation of this guy is equal to a ratio of two partition functions. And again, as Franco told us, this expression, while nice, has the disadvantage that it's not a probability. Okay? So how you remedy that? It can be remedied by using the product measure of two sourceless guys and using the switching lemma. But I'm not going to talk much about the switching lemma, so I won't introduce this particularly today. But I am going to introduce my players one by one. So we have this Ising measure, we have this random current measure. This random current measure almost looks like a product measure in and of itself, except it has this interaction term. But we see this interaction term is really only a statement about the edges in which the current takes an odd value. This has also been mentioned multiple times. For instance, Martin sort of mentioned it. So observation. So this is, of course, I mean, it's a bit of a vague statement, but it can be made fairly precise. So basically, if you take your current and map it to eta, where given by eta of E, just the indicator that n of E is odd, then what do you see? Right, if I take my random current measure, and I ask, under this measure, what's the probability of drawing a given eta? Well, eta tells you exactly what the odd edges are, and you see the even edges are not interacting, but also the exact values of the odd edges are also not interacting. As soon as I know what the odd edges are, then there are no further constraints on the model. So what's this probability? It's sum over those currents for which this particular eta is the odd part. And what do you get then? Well, then you get the, well, beta to the NE over NE factorial, product over edges. But now I can lose the indicator. Simply informing you that N is the odd, eta is the odd part already tells me that the indicator is satisfied. And then, well, now what are the constraints? Well, the only constraints is choosing the odd and the even numbers. If you do a quick calculation, this is sum over n, eta is the odd part, or sorry, this becomes cosh beta to the number of, to the complement. Times sinh beta to the edges that I keep. Right? This is just the sum over the even terms. This is just the sum over the odd terms. And then if you simplify this a bit, you actually get that this is proportional to tangent hyperbolic beta to the edges in eta. Of course, there is an indicator that the sources of eta should be at the empty set, if I took the empty set. Otherwise, I have this A, source set A, and I could get this, do the same computation and actually get the same equality of partition functions. Again, just because those partition functions would be the same up to this global factor of cosh to the number of edges. And again, has the same problem that it's not a probability, so it's not like pulling this out of a hat immediately makes you think, oh, now studying the Ising model is much easier, but it's just saying this is sort of the interacting part. And I will be talking about this guy today because he does stand in a particular relationship to the double random current. And finally, of course, we have our FK Ising model. All right, you have the random current. There are two naturally associated models, namely the odd part and the double current. And our favorite other representation of the Ising model is the FK model. It's also been introduced. Which has this interaction term 2 to the clusters of omega, possibly with boundary conditions where the plus boundary conditions only counts the clusters that don't intersect the boundary, supposing we're on a finite graph with a specified vertex boundary. Okay, so this is the slew of models that we will, with which we will spend our time today. And there's one paper that has been referred to multiple times this week, which is, so of course, all of these formulas are an infinite volume, but you could justify taking infinite volume limits of all of them. And you could define this plus measure for the other guys. This is, so to speak, if we consider G a finite subgraph of some infinite graph, this is just the measure that you get by taking the infinite graph and quotienting out by the complement of G. Okay, but where does the interest in the ends of the current come from? Well, if I look at a graph which is amenable, transitive, and locally finite, and possibly in the long range setting, then phi plus is equal to phi for all p. Okay. Oh. So right, boundary conditions don't matter for the random cluster model. Equivalent, you can make this a statement about 2-point functions in the Ising model with free versus plus boundary conditions. And how does the proof goes? Well, what he proved was basically, suppose the phi plus is not equal to phi to the free measure. What happens then? Well, there are consequences you can draw for the random cluster model itself, but they're sort of weak. So one quick consequence that you do draw is that this measure percolates. If this measure doesn't percolate, they can be different. But that's basically all you get. You also get that the edge density of this guy is bigger than the edge density of this guy. But again, this is sort of not very concrete. But what he did prove was, well, now you could look at this sourceless plus measure. Maybe I should just call it the plus measure. Right, so this is the double current corresponding to the Ising model with plus boundary conditions. And again, it's given by, well, on a finite graph, you mod out by the complement, so it becomes one vertex, and then you take a limit. Maybe I should give myself more space. So what does he prove? He proves that some event must have positive probability. So if these two things are different, there is at least one edge such that in infinite volume under this plus measure, there are cut edges that separate infinity from infinity. So this, I mean, I'll introduce ends in the sequel, but this basically says the plus measure is two-ended. Yeah? Of the what? Oh, I mean, so if G is amenable, I will come back to this in a second. If G is amenable, then it can only be intransitive, it can only be one or two-ended. Yes. But I guess at p equals 1, plus and 3 are the same. Okay. So I'd just like to highlight briefly the info here, which is boring in this part of the picture. Right, so he says there is an edge which cuts infinity from infinity. It's not hard to convince yourself in the single current this has to be an odd edge. Given that it's an odd edge, sort of by the same thing I said over here, once you know that they're odd, their exact values don't matter, then asking that it be one is for free. Like there's some edge with positive probability is odd, separates infinity from infinity. Conditional on this, there's positive probability that it's exactly one. But the other conclusion he drew is not for free. I mean, all of this relies on plus not being equal to free, but so now what did he also conclude? He concluded the same for two currents, one of which is the plus current and one of which is the free current. Maybe I should just write it like this. So you take two independent currents, one is like the wired measure and one is the free measure, and you actually see, you get the same conclusion for the sum of the sources. And this is not for free, right? What does it tell you? I mean, let's just draw it picturesquely. So both of these measures are ergodic in the transitive setting. So if in infinite volume you have positive probability, you must have a density of such edges. And between them, you have some sort of spaghetti. Okay, but you know that these edges have to belong to the wired current because there's a density of, I mean, at least by thinning out, there's a density of such edges in the wired current. This uses uniqueness of the infinite cluster, by the way, right? You're amenable, so there's only one infinite cluster. There's a density of such edges that cut off infinity in two directions, and the sum of the sources here is 1. But this implies that if I look at the other factor here, it can't percolate. Right? If it percolated, you wouldn't expect the value of the sum of the currents in these edges to be 1. You would expect it to be at least 2. And it plays a big role in Alan's proof. I mean, he says, suppose that these two things are the case, then basically he proves it's a case distinction, it's a proof of case distinction, but in most of the cases he just ends up concluding on most of these edges the sum of the current should be at least 2. So what does he get? P plus percolates and is two-ended. And the free measure does not percolate. So it's also not two-ended. And then basically what he, so call this assumption A. That's not exactly, I mean, he calls this assumption A. But he proves that this is contradictory. Like the plus and the zero current can't be so different that one it percolates and is two-ended, and the other one just doesn't percolate at all. Okay, I am not here to give a new proof of Alan's statement. I would love to, but I don't think the methods I'm going to talk about today, or I mean, I think something like the methods I'm going to talk about today could give a new proof, but certainly not the argument that I'm here to give you today. Okay. So what are we going to talk about? I'm going to talk about, okay, so I am, it sort of follows from what I'm going to say, but I'm not going to give any details on it right now. And I mean, there are other means to prove this, but if these two are the same, this does imply that P0 is equal to P plus. So basically, for the future, if you know that phi plus and phi, the free phi are always equal, then you can help yourself to saying any question that I want for the double random current, I'll just pretend that both are sourceless. Or I mean, I'm free to help myself to the fact that both are sourceless. What I'm going to talk about today applies equally well for wired, and sourceless, if you'd rather think of the world in which Alan's proof had not been proven. But I'm going to talk about ends. Why am I going to talk about ends? Because the theory, okay, so this might just be a pipe dream on my part, but I am sort of hoping that one day we could have a theory of ends of percolation configuration, of percolation measures. So think about it this way. If I'm on a transitive graph, okay, you can use ergodic theory to talk about the number of infinite components. If I'm on a general graph, even for Bernoulli percolation, I'm not entitled to think that there's a fixed number of infinite components. And I mean, it's very easy to construct examples where this is false, but for Bernoulli percolation on any graph, the number of n's is a deterministic thing. So maybe I should just define what I mean for graph G. The number of n's is the biggest number of infinite components that you can obtain by removing finite subgraphs. So in all of these cases, the finite subgraph you can remove is just a single edge. And just so we're all on board, set D has one end when D is at least 2, and set has 2. Okay, basic examples. The D regular tree for D larger than 2 has uncountably many ends because they form a Cantor set. Right. So let's just remark what I said before to Subhajit. If G transitive, there are only 3 possibilities, namely 1, 2, or infinitely many ends. Why? Because suppose somewhere you had some finite graph where upon removing it, you obtain 3 ends or 3 infinite components. This picture does not look very transitive, but this is my lack of drawing skills. Supposing you get this picture somewhere and your graph is even quasi-transitive, then you must get the same picture somewhere else. And I knew here, because this separates 3 ends, that this guy and this guy are not connected outside, so at least one of these 2 guys is a new infinite component. Right, so once you have at least 3 ends and you're transitive, these will sort of explode. Why am I mentioning this? Because you get the same thing for percolation configurations. So if you're an ergodic percolation measure on a transitive graph, then you can either have 1, 2, or infinitely many ends. Why? For the same reason. Suppose that there is positive probability that you branch of 3 ends at some point. By ergodicity, you have infinitely many places where this happens, and this sort of branches off. And of course, Burton-Keene is going to come in and say infinity is not an option if G is transitive, amenable. Right? It's just looking at Burton-Keene and convincing yourself it rules out regions that look like this just as well as it does normal trifurcations. You can't necessarily help yourself to an actual trifurcation because nobody told you that this measure had nice properties. So I'll just briefly remind you, what's the foo? Right, so this is sort of implying I requested a theory of ends that works sort of beyond the ergodic setting. This is sort of still using ergodic theory to conclude something about the ends. I'll just briefly remind us what this ergodic theory says for the number of ends.
Ulrik?
Yep.
I didn't really understand the G is transitive 1, 2, or infinitely many ends. Can you just repeat it very quickly? So what's the picture there?
Right. So suppose I have one place where 3 infinite, if I remove this finite subgraph, then the complement has 3 infinite connected components. They're distinct, and there are these 3 guys. You're transitive, so this picture repeats itself somewhere. These guys are not connected to here outside of this orange region, so these 2 new guys are new infinite components. It's the same thing that happens in Burton-Keene. Why do you need trifurcations? Why don't bifurcations work? Because bifurcations don't explode like this. It's exactly the same reason that set is two-ended and all the other irregular trees are infinitely ended. Okay. So just to briefly sketch. So there are only, if we're in this Aran setting where we're amenable and transitive, then there are only two possibilities, 1 and 2. How does this normally go? Well, 1 and 2 per component. I have not said that the components are unique, yeah?
Can I ask a quick question?
Yes.
Is this using ergodicity or not? Because I think if you...
Is this ergodicity or not?
Yeah, because if you have 3 ends, then you...
No, this is ergodicity.
Okay.
Right, if you're not ergodic, you could have any number of ends you want.
Okay.
If you're not translation invariant, yeah? Yeah. But if you're not automorphism invariant, yes. 1 and 2 are the only options for right. And I guess I slightly lied here because how does this voodoo normally go? So I lied slightly just before. So of course, normally when we're doing this sort of Burton-Keene type argument, we're using insertion tolerance to deduce that the number of infinite components is 1. So there's a unique infinite component. With the most 2 ends. For percolation, you would never really think about this, but what it's the other side of the picture. If you're deletion tolerant, meaning, right, conditional on everything outside of a box, I'm free to delete all of the edges inside at a positive probability, that's all you need. Then you conclude 1 end. But if you don't have this, there's no generic argument to get you to the 1-ended case. And what's the problem with this guy? So as you see, the odd part sort of has this cosh flapping around because the even edges are independent of everything else. So those I can add. So the measure is insertion tolerant. But there's not deletion tolerance because this guy is not deletion tolerant. Why is he not deletion tolerant? He has to be an even graph because there are no sources in the original current. But even graphs cannot be deletion tolerant, right? If I reveal to you the configuration outside of a single edge, then I can tell whether the edge is open or not. It's no deletion tolerant. Okay, so why am I obsessed with this? Well, Frederick and I are fairly obsessed with this zoo of graphical representations of Ising. So now I'll just delete what I wrote, but draw a picture instead. Okay, so the first model was this even percolation. It's x is tangent hyperbolic beta. That's a bit of a hassle to write. I usually just write x. And it's related to the single current, which I usually do parameterize by beta because that's the nicest parameterization here. And getting from below to up top requires taking the union with a given percolation, right? You take this guy, these are the odd edges, all the even edges are independent. You just add those independently at random with some parameter that you can figure out. It's not super important what it is. There's some parameter that does this. What about my phi, which I usually parameterize by p? P is 1 minus e to the minus 2 beta, but there's some parameter that makes this work. And there's a similar description here. If I want to get from the odd part of the current to Fk, I also add an independent percolation, but with a different parameter. I guess in my life, what's important here, I guess I should say this is the trace. So I mean, I forget the values of edges. I only remember which ones are open, which ones are non-zero. One can note that this x is bigger than this 1 minus square root 1 minus x squared. I guess that's the only part where the parameterizations are really important. And then there's the last guy, this double current, where, okay, the arrow here is easy. Oh, I guess I should say this parameter is bigger than this parameter, so there's some independent percolation that you can add here. I never remember what the parameter is because that's not important in my life. But right, this parameter is bigger than this, so it's just a basic fact. You sprinkle some of the way to get here, you sprinkle some more, you get here. There is some independent percolation that you could add on top. What's the thing you should add here? You should add an independent copy of the sourceless current. What's this arrow then? Well, this current is already odd part plus a percolation. So in this picture, I think it's nicer to say I should take a union with another odd part and then a percolation. And this factor is super not nice. 1 minus square root 1 minus x squared, who cares? But if you do the computation, if you take two independent one of these and put them on top of one another, you get percolation in parameter x squared. Okay, so this is my initial SU, but this mostly is good for transporting negative information, say from up top to down here. It says both this measure and this measure stochastically dominate this measure. That's often not super useful because we understand, say, the subcritical phase of our models very well. What is useful, or that I will claim, is that you can go the other way. And sort of, I don't know if you consider this magical, but these two arrows are the same. You take an even subgraph uniformly at random. So what does this mean? Usually I write down some notation and then it's a bit too heavy. But what it means is you sample a guy according to this measure. That's a graph. From this, you could take an even subgraph uniformly at random amongst all the ones you have. The things that are sampled has this distribution. And the exact same is true on this other side. I sample the trace of the double current. From this, I pick an even subgraph uniformly at random, and that has the distribution of this guy. So this we attribute to, so I think everybody in this community who's aware of this learned this from Grimmett and Hanssen. In 2009, but thanks to ChatGPT, we found an earlier reference with the same statement. It's like significantly earlier, but these are physicists, and I guess you need to know that their papers, these guys have more of a computational bent, so I guess it's natural that I have no impression that Jeffrey and Svante knew about this other paper. What about this other thing? So Marchin computed the law of the trace of the double current. It's not too bad to think Lorca may correct me, but was this published in 20 and put on the archive in 18? Okay, I'm gonna say 20. But the first paper where you can see this written down is by Frederick. But again, neither of these tell the full story of what I need for today. What I need for today, I was going back and forth as to whether this would be the reveal at the end. Actually, all of these arrows are part of one joint coupling. Meaning, so this is a priori saying there's one coupling from going up to here, to, like one coupling of these two guys where I start with one of these. I take independent copies of these, add them all together, and then that guy will be a double current. And there's another coupling where I start with one of these, I take a uniform even subgraph, output this guy. But those are the same coupling. Under each of these couplings, if you look at the conditional measure of the guy you didn't start with, if the guy you started with conditioned on the guy you produced, then you actually get the other arrow. This is going to be important. Okay, so this is some connection between these models. and I have 10 minutes left. So I should be quick. So I can wax poetic about the joys of the uniform even subgraph, but this turns out to be a somewhat nice measure. 15? I mean, I should still get to the proof. So I'll just briefly mention. So if I look at my even subgraphs, of course, they're a subset of 0, 1e, right? This is just my normal space of percolation configurations. Now, something we never say because it's usual percolation is never useful. This thing is a group. It's a group in a way that just spits you in the face, right? 0, 1 is just set mod 2 set. That's a group. There's a group operation. And taking a product of groups gives you a group. It's even a compact group. Taking a product of compact groups gives you a group. But this guy is a subgroup. All the even subgraphs form a subgroup. What's the group operation? It's just XORing. And we do use XORing from time to time. So, I mean, it's not like it's been hidden all this time. Why am I saying this? Because when I mentioned the coupling here, all these couplings make sense in infinite volume. Right? This is a compact group. It just has a uniform measure, no matter what my graph is. It has a subgroup that I call the free even subgraphs. So this is the closure of the finite subgroups, finite even subgraphs. So these are the finitely supported even subgraphs. And my claim is these are the same if and only if G is one-ended.
Sorry, what do you mean by closure here?
Take the pointwise limit. So everything I could get by take a sequence of finitely supported even subgraphs, look at the pointwise limits. Right, this space comes with the topology sort of inherently. Okay, and moreover, so this is a theorem by myself, Ulrik, Ulrik. And this really is from last year. Like the original paper was in the archive in 23, but this theorem was only added last year. So this is no matter what my graph is, I can tell you what the extremal Gibbs measures of my UG are. And they are exactly in one-to-one correspondence with this quotient. Basically, this set acts on any Gibbs measure, and then you just characterize how many, right? You reduce to a set of even subgraphs that have a unique invariant measure under this action. It's not a hard thing to prove once you realize that it's tribute true signal.
This is E, wait, what does it say? E0.
Yeah, so this guy is smaller than the big guy and the quotient. So in particular, and this was a bit confusing to us in the original project, if your graph is not one-ended, quote unquote, the thing that would naturally be the wired uniform even subgraph is not extremal, which is surprising because in general it is ergodic. Ergodic, not extremal. Okay, but I'm running low on time. So maybe I should just say what this means in the double current end. So I told you Alan gave a proof that phi plus not being equal to phi free implies something very particular. And say on set D, when D is at least 3, continuity of the Ising phase transition follows from equality of the free and wired measures. But he did not prove that the supercritical, like the infinite cluster of the double current is two-ended. Or is not two-ended. He just proved that if the wired is two-ended and the free doesn't percolate, that's a contradiction. And again, we don't have this deletion tolerance that we normally need, but so the theorem that I would like to prove here is as follows. If G is one-ended, amenable, transitive, and asterisk, well, which hopefully I'll get back to, and this thing percolates, meaning I take two independent sources and I add them. The infinite cluster is one-ended. And the proof is very short, so in my 7 minutes, I should be able to at least sketch it thoroughly. So I am going to use this fact as intuition, but as it turns out, it's not what's going to give you the proof, or at least it's not what we end up using to give the proof. Right. So suppose that the double random current is two-ended. Then it's uniform. I mean, you start with this diagram, and then you would like to say, how does this coupling extend to infinite volume? There are now several possible infinite volume UEGs. So if you hope that this coupling survives, you have to ask yourself, which UEG should I pick in the limit? Right? There are two options. I mean, two extremal options. You could take any convex combination thereof. And what I am going to argue to you is that this identity, right, so two extremal Gibbs measures, of the UEG on the current one, so to speak, with sources at infinity and one without. Basically, that's always how these different Gibbs measures look. They have some set of sources at infinity. You specify those, you get an extremal one. So what I'm going to argue is that, well, I told you this is one coupling, but now for the time being, I'm just going to say I have two identities of measures. The first is the double current is this union. And this is going to imply roughly that that if I take my copy of this odd part inside the double current, this has sources at infinity. Okay, but in finite volume, I have this identity that lupo one is the uniform even subgraph of this guy, and this pulls in the other direction. Oh, but that's contradictory, right? I mean, if you just knew these two facts, now you would be in the setting where you say, okay, I just have two couplings and the two couplings disagree on what the thing should look like, but no, there is the same coupling and they disagree on how this inclusion should look like. Okay? Okay, so let's do the proof sketch. I take a big box inside of a even bigger box. I'm gonna assume, no, I mean, and what are you gonna do? you're gonna choose these scales well. Most things will do because this is sort of soft. Then you're gonna explore the clusters in the double current from the boundary of the big box. And if you chose both numbers large enough, then supposing you're two-ended, you're gonna see two clusters crossing the box. I mean, that's just what being two-ended should mean. So this is with high probability. Okay, but now I'm gonna ask myself, suppose I also don't just reveal what the trace is, but I also reveal what my current does, so I know where my sources are. Then I have some sources here on the inside of the box, but only corresponding to the two clusters that are sort of attached to infinity in the other ends. Okay, but I also know, again, this is just insertion tolerance and amenability, there's only one infinite component. So I know that in the infinite volume measure, when this happens, well, one of these sources, I must be forced to connect this part to this part. It's not good enough to say with 99% probability they're connected. It really has to be with probability 1. And this is where under asterisk, you want to conclude that then in one of the currents, one of the sources has to be odd. It's just, if I have an even number of sources here in both currents, I can just attach those to each other and I don't have to connect, and the similar over here. There is like some combinatorial madness, but in the planar case, you would really use that. This picture has to be good. In the, say, on set D, you would just like carve out spaces for yourself in a big box where you can put your sources. I mean, this is, in all concrete graphs, you can do this easily. But the technical assumption is if the number of sources, like if the box is chosen right, and I have even sources here, and these two things are slightly separated, then I don't have to glue them. So this means at least one copy of Lx has odd sources. In one end. Okay, so that's this implication, right? I have two of these guys, and I'm just saying one of them will have an odd number of sources. Okay, but why does this not imply that only one of them looks like it's sitting inside with sources at infinity? Like you just toss a coin at the beginning, one looks like it has sources at infinity, the other one does not. Well, the product measure here is ergodic. So if there's positive probability that this guy looks like it has sources at infinity, then it always looks like it has sources at infinity. Okay. But this is the punchline. Suppose I'm in finite volume, but super big finite volume, so that I know I can use this coupling. Well, if I chose this guy big enough, then I know the picture here will look the same with high probability. I can make this 99% if I want. And now I'm going to say, well, if I'm in finite volume, it can't be true that deterministically one of my guys has odd sources. Why? Because if it has odd sources, that's because in the bigger graph, there is some loop wrapping around. Okay, but if I take the symmetric difference with this guy, and that preserves the UEG measure, then I flip the parity of the sources. So it's just a statement on any finite graph, the parity of the UEG at such a cut set can at most be odd with probability a half. This is true on all finite graphs. So it doesn't even matter that I haven't explored it in here. I'm just saying either there will be no loop going all the way around. In this case, it's deterministically even, or there is a loop going all the way around, then it's probability a half. And again, you're going to use ergodicity to conclude that then it's zero. All right. So the first thing, I mean, you're going to use ergodicity to finish the job. So you're going to say, this thing says I have sources at infinity with probability 1. This thing says I have sources of probability with probability 0. This is a contradiction, so therefore I can't have two ends. And that's all I wanted to say. Thank you for your attention.
Any questions either in here? So I missed I
Yes.
a bit lost at the punchline.
Yes, that's okay.
Could you just repeat it again?
Yes. So there's one so I just give you a chunk of a finite piece of window in which I see two crossing clusters, exactly two crossing clusters. And now I'm basically saying, if you look at this in infinite volume and you look at this in finite volume, you actually get two different conclusions. And the two conclusions you get by first using this perspective, and the other conclusion you get by using this one. So the first one, I'm just saying, well, my current is just a union of these guys. So now if I reveal to you my sources on this random domain that I've picked, well, if I'm two-ended in infinite volume and I have a unique infinite component, then the sources must be such that I have to connect from the one to the other. Meaning, so it's a double current, so I have two of these guys to work with. So the conclusion just becomes one of them must be odd under very reasonable assumptions on the graph. Okay, so almost surely when I reveal such a picture, it's because one of my lupa1 guys has an odd number of sources both here and here. And then they must be connected to each other. But if they have an odd number of sources on this guy, I can tell in which coset they lie here. This is like a local to global effect. And this implies, it doesn't imply that you're a particular uniform even subgraph. It just implies at least one of them, seen as an even subgraph of this guy, has sources at infinity. Just sort of because you take another set and you see that the number of sources, the parity of sources here must be equal to the parity of sources in the other set. Okay? And ergodicity, so I mean, then the conclusion is the only conclusion you can really draw from that a priori is that for this guy with probability 1/2, it has sources at infinity under this coupling. But then you're going to say, oh, but the product measure of these guys is ergodic, so therefore the probability is 1. It's not 0, so it must be 1. Now, for the other part of the conclusion, now you're going to say, I'm going to ignore that there's an infinite volume picture somewhere. I'm just going to say, this is a subgraph of a finite graph. Now I'm going to say something about uniform even subgraphs of finite graphs. And there I'm just going to say, if you have a cut set somewhere, the sources of your uniform even subgraph on that cut set can be at most 1/2. Because either you're going to have this loop winding around, you can XOR with this flips the parity, or there's no such thing, then deterministically the number is even. Then the probability is the most 1/2, you use ergodicity to conclude it's 0.
Any other questions?
Do you have like, is it possible to just to say something of the form like, if my graph has more than one end, then it has multiple UEGs basically?
Yes.
This is the principle that you're using.
Right. I mean, in the end, all we're using is that the set of even subgraphs, just as a set, gets sliced up into two subsets that I can distinguish by local combinatorics. I mean, it also has multiple UEGs, but that's because there is a free even subgraph invariant measure on each one of them. So they must be the extremal ones. Free and wired what? I don't know that the free and wired UEG of, no, I mean, if you suppose this is two-ended, then the free and wired UEG are different. But we actually, upon looking at this, we figured out it's actually harder than one would hope to prove that you get for free that the UEGs are Gibbs measures of lupa1. This is not for free. Why? Because it's not true that if I have a locally convergent sequence of graphs, then the UEGs are weakly converging these measures. That's just not a true statement. It is true if the limit graph is one-ended, but that's basically because there's only one thing they could converge to. But if there are multiple things they can converge to, then you're in trouble, especially if you try to, I mean, we work around this by like squirrel cut embedding. Then you really have a problem. If I start with a configuration converging pointwise, then I can thin to a random subsequence for which the UEGs converge, but this a priori depends on the realization. And I think this is, I hope that there is a way to tame this, but it seems like you would really have problems with like the discontinuity of the UEG.
So sorry, I have two more questions.
Yes, go for it.
One is, what is the star in your theorem?
What? Yes, the star is, right. The star is, you must be sure that if I have an even number of sources, like in both parts, then they won't be connected deterministically.
Say that again.
Right, so I mean, for this part, you need to conclude that unless one of the source sets here is odd, then I'm not guaranteed to connect. But this is like a deterministic statement about the even subgraphs of this small box in the middle. Okay. Basically, worry is something like 3 regular non-planar graphs. I mean, it's really, okay. I didn't want to get bogged down on convincing you that you construct this. It's, in any graph you can come up with that's reasonable, this is true.
Okay. And the final one is just single random current.
No, it does not.
What's your guess about the single random current?
So I stated an open problem this Monday that if you're, right, so this measure is nice in that it has FKG insertion tolerance, deletion tolerance, everything you would want to ask for, and it's one-ended. So I believe that if you take a UEG of a graph, like any graph, then either the UEG will not percolate, have the same number of ends as the original graph, or have infinitely many connected, infinite components. That's my guess. Don't ask me how to prove it. I would love to. And if you have that, then there's a one-line version of Alan's paper. Or I mean, Alan proves his one thing. If they're different, then the wired measure must be two-ended. Then you say, well, but you're the UEG of a one-ended graph. I mean, if the single current is two-ended, then the odd part is also two-ended. And then you say, well, but the odd part is the UEG of a one-ended thing. So that can't be.
Okay. All right. Any other questions, either online or in person? If not, let's thank Ulrik again for a very beautiful talk.